Hey dude, let's go over lab 3. Let's talk about series circuits, or more specifically what you're going to be doing in the lab. You're going to be building your circuit with these resistors over here. 100, 200, and 800 ohms. And as you know, a series circuit, because you just watched the video on series circuits. Yeah, I just posted a video on series circuits. So, so we hook them up like this. So they're a series because the current only has one path, and this is how we hook them up. Now, the total resistance is this value plus this value plus this value, and that's the formula. So that's also, I walked through that in my video as well. So what you're going to do is you're going to hook up the circuit, you're going to take some measurements, and you're going to see if Kirchhoff's voltage law for a series circuit actually makes sense. Kirchhoff's voltage law for a series circuit is the voltage drop across that plus the voltage drop across this plus the voltage drop across that equals the voltage source. And it should, but it won't be exact. We'll talk about that in a second. So, and you know that a voltage drop exists across a resistor because voltage is W over Q. And we know the problem there is essentially we're losing voltage. That W, which is energy, makes the energy goes away and we have less voltage. So it takes energy to push the electrons through this resistor. So therefore we've lost energy, so we have less on the way out at this point right here, so the voltage is less because voltage is energy per coulomb. So we know there's a voltage drop there, a voltage drop there, and then the last voltage drop over here, we're using up all of the energy to go through. There's none left when we go here, so their voltage potential at this point is 0. Okay, so with that said and done, you're going to build this circuit. This is your variable DC power supply. You'll set it to the voltage that's set. The voltage is right here. Sorry, what is the voltage? It'll come later. So, yeah, and this is just a concept of how we're measuring current. So when we measure voltage, we measure across this. We measure it in parallel. But when we measure current, we have to physically break the current and make the current go through the meter. So you're going to put a meter in here and a meter in here and a meter in there. So you're actually going to physically remove the banana clips, the wires, from the actual circuit and plug it into the DMM. Cool. So, and you're going to see that the current here and the current here and the current here are it's all of the same, because in a series circuit, because you watched the video, you can see that the current is the same everywhere in the circuit. Cool. So what I need you to do is always use measured values in calculation. Did I say always? Yeah. Always use measured values in calculation. So what I want you to do is take the resistor, like do not hook the resistors up just yet. Measure their value and like use all of the digits. Measure all of the digits and put them here in your chart. So put your value there, your value there. And then I actually suggest that you hook them up in series and then actually measure the total resistance. Write that down. So now you have 4 resistive measurements, one for each of these and then the total. So once you do that, measure the total resistance of 3 resistors. Oh yeah, okay, from points A to D, so A to D, that's cool. And also then I want you to actually add them up. So show your calculation. So what you do is you take the formula that's RT is R1 plus R2 plus R3 and add them all up with units. Make sure you, should you put units in your formulation? Yeah, maybe. Cool. And then what you can do is you're going to say measured and calculated. And what I mean here is that like you're going to take your measured value and you're going to like I can't write on the screen here. So your RT is equal to measured value plus a measured value plus a measured value. And that's going to come up with some number. And you actually write that here. That's your calculated number. Over here is your actual real total measured value, which was from points A to D. It'll differ just to a small amount, but it's generally going to be the same. They're not exactly the same because they're a bunch of decimals that you don't have, that you can't put in your formula. So they're not going to be exactly the same, but they're going to be generally the same. Cool. So Kirchhoff's voltage law, hook up the circuit, plug it into a power source. It looks like it's 18 volts. And you know the actual values here. You're going to measure the voltage drop across that, measure the voltage drop across, measure the voltage drop across that, and write them all down here. And then measure A to D. Okay, where's A? A's over here, D. You're going to measure actually the voltage drop across everything. Again, just like resistance, you're going to measure the total resistance across everything and measure each resistor. You're going to do the same thing here with voltage. And then you're going to do some math. And you're going to see that the calculated and the measured are not quite right. do your math here, pardon me, and then over here. So the actual calculated value is going to be the measured value plus the measured value voltage, those three measured voltages. And then you're actually going to measure all of it, like Vs. And that's going to be, essentially, it's going to be your one probe is here and the other probe is there. And that point over there is actually this point over here. So you're actually measuring the voltage drop across, or the voltage potential for Vs. And you will see that this plus this plus this does not actually each equal this measured value. It's not going to be exactly the same. Is it exactly the same? No, it shouldn't be. If you get exactly the same number, then you get it. It's okay. Yeah, so no, and it has nothing to do with the tolerance of the resistors. It's actually the fact that when we measure resistance, or we measure current, or we measure voltage, there are actually errors in our measurement. Cool. So yeah, you've got an error here, an error there, and an error there. And if you measure, yeah, the current here, there are all actually going to be pretty much the same value, but you'll see that it's a little bit different because of the connection is not as strong, and maybe the wire, as you physically move them, they lose or gain a little bit of continuity or some resistance to a very small degree, but it affects the current just in a small amount. Cool. So this here, to establish proof, we look for general trends. Yeah. So pretty much, if they're not going to be exactly the same, but you're going to see a general trend if they're all the same. So have we actually proved that Kirchhoff's current law for a series circuit works? Yeah, because they're almost all the same. So the answer is yeah, we've proven it because there's a general sense that that is true. Cool. So over here, kind of stepping into Ohm's law a little bit, you're actually going to AD voltage source, because you're actually measuring the voltage source. And then the total resistance, that should be the measured value of the total resistance, the actual measured value of the total resistance. Not like you measured this resistance, and this, and you added them all up. No, it's like you measure all of them together with no voltage source. And that's the value here. Yeah, because you use measured values in your oh, did I say that? Yeah, in your calculations. Yeah, always use a measured value. Cool. So in Ohm's law, essentially what you're doing here is you've got the voltage, the full voltage source, and you have the total resistance, measured value, and then you use Ohm's law and you calculate the current. And your calculation of current, again, oh, should you use units in your I wonder about that. Yeah. So that value is going to be close to this value, but it's not going to be exact because you're using a measured value and you're dividing that by a measured value. The measured value has error, and this has, the other measured value has error. So you're dividing a number with error divided by another number with error. So your other number is actually going to have a multiplied error, which is not as accurate actually just measuring the current. So the question here is, calculate, yeah, do your calculations, and then are they exactly the same? No, they shouldn't be. But are they same? Are they pretty much exact? Like, sorry, are they close? Yeah. And that's your lab. Okay, bye.